Have you ever stopped to think about the journey a simple medical tool takes before it ever gets near you? It goes through this intense, invisible process that's absolutely critical to keeping us safe. We're talking about sterilization. Think of it as this unseen guardian, a hidden science that makes modern medicine possible.
So let's start with the big question, right? When you get a shot or you're in a hospital, how are you so sure that everything is perfectly, completely safe? How do we know without a shadow of a doubt that it's free from any nasty microorganisms?
Well, the answer is pretty dramatic. It's basically this high-stakes, high-pressure race against invisible enemies. And in this race, winning and losing is measured in fractions of a second and single degrees. It's all about absolute precision.
And here's the official goal. Sterilization is a validated process used to make a product totally free from living microbes. Now that word, validated, is the key to this whole thing. It's not enough to just say it's sterile. You have to prove it scientifically every single time.
So let's pull back the curtain and see how it's actually done. We're going to dive deep inside the sterilization cycle. And you should know, this isn't just some big washing machine. It's way more like a finely tuned orchestra, a symphony of steam and vacuum.
And here's the sheet music for that symphony. This is the high-pressure, high-vacuum cycle. You can see it starts with a blast of steam, then these vacuum pulses suck out all the air. Then, and this is the important part, it hits the plateau phase. That's where the real work gets done. And finally, a drying phase to finish it all off. Every step perfectly timed.
Okay, let's zoom in on that plateau period, because it's the main event. This is the critical window where sterilization happens. But it's actually two parts. First, there's the equilibration time, which is just getting everything up to the right temperature. And then comes the really crucial part, the holding time.
And this, the holding time, is the moment of truth. This is when every single part of what's inside that chamber, every nook, every cranny, has to stay within this super strict temperature range. This is when the microbes are actually being destroyed. Yeah, getting this part perfect, it's literally everything.
But you can't have a successful holding time without the right weapon. And for this job, the hero of the story is steam. But, and this is a huge but, you can't just use any old steam. You need the perfect steam. And creating it is a whole science unto itself.
So, what makes steam perfect? Well, it all comes down to three incredibly important qualities that have to be controlled with pinpoint accuracy. We're talking about its dryness, something called superheat, and the amount of non-condensable gases mixed in. Let's tackle these one by one.
First up is dryness. It's pretty much what it sounds like, how much actual water is in the steam. And you've got a real Goldilocks problem here. If the steam is too wet, everything comes out soggy, and it's a failure. But if it's too dry, you get superheat, which, believe it or not, is also a massive problem.
And get this, the target for dryness actually changes depending on what you're sterilizing. If you have soft, porous things like textiles, you need at least 90% dryness. But for hard, metal loads, you got to get that number up to over 95%. It's a different recipe for every job.
Okay, on to the second quality, superheat. Now, this one seems weird, right? Wouldn't you think hotter is always better? Well, not in this case. Superheated steam is so hot and dry that it acts more like a gas. It can't condense onto the surface of a microbe to transfer that killer heat. It basically just blows right past them without doing a thing.
So how much is too much? The limit is unbelievably tight. You cannot go more than 25 degrees Celsius into superheat. Anything beyond that, and your steam is useless. The whole process fails. I mean, think about that. What a tiny margin for error in such an extreme environment. And that brings us to our third and final ingredient, non-condensable gases, or NCGs. Think of these as party crashers. They're gases, mostly air, that get mixed in with the steam, but unlike steam, they don't turn back into a liquid under pressure. They just hang around, causing trouble.
So why are they so bad? Well, imagine these NCGs creating tiny invisible air bubbles on a tool. These bubbles act like little protective shields for bacteria, stopping the hot, wet steam from ever even touching them. They literally prevent the killer steam from reaching its target.
Because of that huge risk, the tolerance for these gases is practically zero. The absolute maximum allowed is less than 3.5%. Just another reminder of the insane level of precision needed to get this right every single time.
All right, so we've designed our cycle, we've perfected our steam recipe, we've run the whole thing. But how do we know? how do we prove with 100% certainty that it actually worked? Well, now we have to pass the ultimate test. This is all about validation.
And success here is not up for debate. It's measured by two and only two things. First, you have to prove that you maintained perfect temperature control through the entire cycle. And second, you have to prove that you could defeat the toughest microbial opponent you can find.
And check this out, the rules for temperature get even stricter as you go along. In the first minute of that critical plateau phase, you're allowed a 5-degree difference between the load and the chamber drain. But after that first minute, for the rest of the holding time, that tolerance shrinks to just 2 degrees. The system demands perfection.
But all the temperature data in the world is only half the picture. The philosophy here is simple. To be sure you've won the fight, you have to beat the strongest challenger. So to really test the cycle, scientists put something inside on purpose, something they know is incredibly hard to kill.
Meet the undisputed heavyweight champion of heat resistance, Bacillus styrothermophilus. We're talking about placing test strips inside that are covered in more than 500,000 of these ridiculously tough spores. Their D-value, that's the time it takes to kill 90% of them at 121 degrees, is over 1.5 minutes. The thinking is, if your cycle can kill this bug, it can kill absolutely anything. It is the gold standard for sure.
So the next time you see any kind of sterile medical product, you'll know the incredible invisible science that went into it, that symphony of steam, pressure, and time that guarantees our safety. It kind of makes you wonder, doesn't it? What other invisible processes, built on this kind of mind-boggling precision, are out there protecting us every single day?